Hi, everybody. So, welcome to part three in our lecture series on light. Um, so, you might notice that my background here is a little different. Of course, I'm not actually in outer space. I'm actually using Zoom special features where you can create a virtual background. And the reason why I have that is one, it's cool, and two, um, my background's a little messy. So, trying to have fun, but also cover up my mess here in the back, if you know what I mean. Okay, so today's discussion is going to be on how light interacts with matter. Okay, so let's just jump right in here. So um, it's always good to ask why you're learning what you're learning, right? And so, why is it important to learn about how light and matter interact with each other, right? Um, and it's a simple reason because if light and matter didn't interact, these two things would not happen. You would not be able to see, right? Because light is interacting with your eye, and then your eye interacts with your brain to feed it the image that you're seeing. And then life itself would not be possible. So that one's a little bit more dire because light is what plants use to make their own food via the process of photosynthesis. So, very, very important on why light needs to interact with matter. It is actually very vital for life to occur. Now, there's going to be a lot of background information that you need to know. Some of it might seem like a review. Maybe you've taken like a high school chemistry class before or a high school science class. If it is, great. That means a lot of this stuff will be familiar to you. If not, then pay attention because this is going to be forming the foundations when we talk about other specialized topics in astronomy. Okay, so in order for you to understand how light and matter interact with each other, you need to be able to understand um, how light is being produced in the smallest structures in nature. Okay, so this is kind of humbling, right? Because like astronomy is usually the study of like the biggest, most massive objects, and we're seeing the light coming from those large objects. But then you got to study the little tiny objects to figure out how that light was actually produced. Okay. Um, and so, kind of going back to the previous lecture that we had, um, how do you produce light? Well, light is pretty much produced by charges that are speeding up, slowing down. Essentially, like they're like moving charges, and they're always changing their motion within matter itself. And so those charges are going to be contained in the tiniest particles within matter. And some of the tiniest objects are called atoms. So, atoms are the smallest particle of an element that makes up matter. So, they're like the basic building blocks of what makes everything up that has some sort of mass. Okay, so they're very, very tiny particles. Um, and for example, just to tell you how abundant there are, 1 teaspoon of water contains about 10 to the 23 atoms. So that's about half a trillion atoms, right? That number might sound familiar to you if you've taken chemistry, 10 to the 23. For you chemistry nerds out there, that's basically Avogadro's number is what I'm pertaining to. You might have also heard, the quote about how many atoms there are. So, for example, there are more atoms in a teaspoon of water than there are teaspoons of water in the whole Atlantic Ocean, which is, again, just mind blowing in terms of how many atoms there are, okay, in a teaspoon of water. Okay? All right, so within an atom, are many tinier objects. And so we're going to have to get a handle on how the structure of an atom looks like, because that's where the charges that produce light are going to be contained. So here is like the modern view of what an atom looks like. And it's essentially three objects. You have a proton, shown there in the red. A proton is basically a positively charged particle that lives in the nucleus, and the nucleus is basically residing at the very center of the atom. And then you have neutrons, which have no charge at all, also living in the center of the atom, the nucleus. And then you have the electron. So electrons, they don't live in the nucleus, they're actually outside. And we we kind of view the electron as this negatively charged cloud that kind of is blanketing around the nucleus. So we're going to go back to that in a second in terms of why the electron looks like a negatively charged cloud. Okay, but first let's talk about how you can have different types of atoms. So you've probably seen a periodic table before, where you have a list of every single element on it, and every single element basically has its own specific type of atom. And so the element that you're seeing in a periodic table, basically you have different number of protons for every single element that you have on there. So just to give you an example, hydrogen is the most basic atom you can possibly have. You have one proton inside of a hydrogen nucleus. That's why sometimes it's kind of synonymous to say, oh, it's just one proton. That's basically a hydrogen atom, okay? Or if you can have, for example, two protons within a nucleus, that is the next basic atom you can possibly have in nature, which is a helium atom. Helium is the atom that composes, the air inside balloons. And then if you have three atoms, like shown here in the picture on the right, then you have a brand new element, and that's called lithium, right? And essentially, that's what your batteries, or at least the newer generation of batteries, are made up of. Okay, so aside from that, now let's actually learn a little bit about how all of these tiny little parts of the nucleus interact with each other. Okay, so here's the key idea. Within a nucleus, opposite charges attract each other. So electrons, they're actually bound to their atom's nucleus via the force of electricity. Okay, so positive charges are attracted to negative charges via electrical forces. And so the thing is that, hey, if you have an electron that is really, really attracted to that proton or the nucleus because it's positively charged, right? Then it's actually going to take some energy. Let's say you were the person in charge of removing that electron, pull it apart from an atom. It's going to take some energy to pull that electron further away or completely remove it from the atom. It's kind of like you trying to, pull apart a piece of Velcro together. You take some energy to pull apart a piece of Velcro because, they're stuck together initially. So you got to put some work in to remove that. Okay. Now, let's say you're actually able to put in enough energy to remove that electron from the atom. And so now you start off with an atom that could be neutrally charged because you have one positive, one negative. They cancel each other out, right? Then if you remove that electron, now you have a net positive. So that means you have now created an ion, which is an atom that either gained or lost an electron. Either way, it's basically an atom that has some sort of net charge or a charge that is not zero or not neutral. Okay? All right. So something that I'd like to kind of revisit here um, is how we mentioned that the electron is a cloud, right? And for a lack of a better word, it's basically a cloud of negativity that surrounds the electron, the nucleus, excuse me. So why is it a cloud? The short answer is quantum mechanics. So from quantum mechanics, you basically discover that everything, even electrons, have particle and wave-like properties. So they basically behave just like light would, okay? And so what that means is that when you're looking at this figure right here, um, where's my mouse? Here he goes. When you're looking at this figure, the dark areas, so the darkest part of this picture is going to be on average where the electron will be found. Okay, so that means that on average, electrons behave like a particle on some sort of fixed circular orbit. But in principle, they could be everywhere in the nucleus. It's just that some areas you're more likely to find them in, and in some areas you're not very likely to find them in. Okay, so they can basically freely roam about. If you've taken some sort of high school chemistry, this is probably the view of the atom that you were introduced with. And this is a very simplified view, and it's actually accurate to some degree. If you're only talking about the average positions of the electron within an atom. However, if you want to get the full picture, again, this is actually what an electron is. Again, it's a cloud of probability, okay? Later, actually, when you do your lecture tutorial, they're going to be presenting the atom in this kind of picture. And so keep in mind that, again, that's just an approximation. On average, you will find the electron in some specific orbit around the nucleus, but it's not really what's actually happening. Okay, just keep that in mind. So something to realize as well is that atoms, as tiny as they are actually mostly empty space. And if you think about the size of the nucleus, so if you look at this picture, let's say this is like your nucleus, right? The size of the nucleus is on the order of 1 femtometer, or basically 10 to the negative 15 meters. So it's a very, very, very small number, or a small unit of length, right? And then the first electron, on average, again, because it's a cloud, is 10 to the negative 10 meters away from the nucleus. So, for example, in this picture, on average, the electron is going to be here where you have the darker regions shaded in. So if this is my nucleus, the electron is like going to be 10 to the negative 10 meters. So this is going to be 10 to the negative 10 meters right there, okay? And this is 10 to the negative 15 meters. So both of those are very, very tiny numbers, but you have to really compare them against each other, because that tells you, right, that there's going to be a 5 order of magnitude difference between the size of the nucleus and then the size of the orbit of the electron that's closest to your nucleus. So that tells you that the electron's orbit is about 100 times greater than the size of the nucleus. Now, why am I saying this? Well, let's actually compare an atom, the way it's organized, to the solar system. Like, let's basically make this analogy where, hey, my nucleus can be like the sun, and then the planets can be like the electrons that are orbiting, right? And for reference, Mercury's orbit is only about 7 times larger than the sun's radius. So 7 times larger versus 100 times larger, right? Huge difference. That's why atoms are pretty much mostly just empty space, okay? All right, so here's the thing. If you were to make the nucleus and scale it up to make it equal the size of an orange, so the size of an orange is about 10 centimeters, right? And let's say you live in Mira Mesa, or actually, when I had this lecture planned out, we would be in a classroom in Miramar College, right? Let's say you place orange in Miramar College, and you ask, okay, where is going to be my nearest electron? So this is the crazy part. The closest electron will be found near the I-805 entrance via Mira Mesa Boulevard. Okay? So that's about like, I don't know, 6 miles away. So again, I stress the idea that, atoms are mostly empty space. So that's kind of a way to understand that to something that you guys are familiar with. Okay, so everyone's probably seen this before, the periodic table. If you watch Big Bang Theory, Sheldon Cooper actually has a shower curtain that is a periodic table, which is kind of showing you like his next level of nerdiness. And so the periodic table, again, you can see here that like you have hydrogen, right? And then number 1 on the hydrogen tells you how many protons there are. Helium has 2, lithium has 3, beryllium has 4, and so on and so forth, right? And so the periodic table, there are specific ways why it looks like that, why it has this weird shape, but essentially it organizes the atoms by the number of protons and chemical properties that there are. So this is astronomy, not chemistry. So we're not going to be required to memorize all these elements at all. In fact, let me show you the periodic table for astronomers. Okay, much, much, much simpler. In the astronomer's periodic table, the most important element is hydrogen because it is also the most abundant element in the universe. Why? Because it's the easiest one to make. As long as you have 1 proton, you basically have a hydrogen atom. Okay? And then the next one is helium. That's why, it's like the second largest font in this periodic table. And really, you have hydrogen, you have helium, and everything else are basically considered quote-unquote metals. So you have gases and you have metals, okay? Very, very simple. And all of these other elements, so these are elements that are going to be naturally occurring whenever stars are growing up. They make heavier and heavier elements inside of their cores, and that's essentially kind of what makes up all the other objects outside of stars. So we're going to talk about that later when we talk about how stars evolve. All right. Okay, so I think this is a good stopping point. And next time, well, let's actually answer our question on how does light actually interact with atoms. See you next time.